Welcome to our third video on our Year 10 Chemistry unit of controlling the rates of reaction. And in this unit, we are actually going to look at rates of reaction. So the outcomes that we're looking at, we're again back at that third outcome, which is observe and understand that chemical reactions take place at different rates. So we looked at that in the collision theory so that we could have an understanding of how reactions occurred. Now we're going to be covering that again through the rates of reaction. And we're going to identify the factors that can affect rates of reaction. We're going to explain the effect of a range of factors, including temperature, surface area, concentration, agitation, and catalysts on the rate of reaction. And we are also going to describe the role of catalysts, it's kind of in the previous one, in some chemical reactions. Alrighty, so rates of reaction, what we're actually looking at is how fast do reactions go, alright, and how can we actually change that? What factors are there that we can adjust to change the rate of the reaction? So the speed of reaction varies depending on the circumstances of the reactions taking place. Some reactions can be really fast, okay, so think of exploding gases. However, others are really quite extremely slow, such as rusting. So collision theory and rate of reaction. So we said that a collision had to occur with the reactants at a certain orientation and with a certain amount of energy for our reaction to be fruitful. So for the fruitful collision, for a reaction to occur. When we're talking about the rate, we look at how fast the reaction will go. So we are presuming that a reaction has occurred. We know, not presume, we know that a reaction has occurred, but how fast does that reaction go? Essentially, the greater the number of collisions between particles, then the more chance of a fruitful collision, and therefore the more collisions occurring, the faster the rate of reaction. So sometimes we need to speed up or slow down chemical reactions. So we actually need that control, okay? For this reason, it's important for chemists to understand how to control the rate of reactions. So we've got 5 key factors that can affect the rate of reaction, and they are temperature, concentration of the reactants, surface area of the reactants, agitation, so mixing, and the use of catalysts. All right, let's have a look at each of those 5. So first one, temperature. How does temperature affect the rate of reaction? If you think about putting a roast into the oven at 40 degrees, it would take a very long time to cook because the process of cooking is very slow at low temperatures. In fact, our roast probably wouldn't cook at all at 40 degrees. However, let's imagine that your neighbour came over and cranked up the temperature to 280 degrees. As you might expect, that roast would cook much more quickly. By the time the stove alarm went off, there'd be nothing more than a smoky lump of charcoal. So we're seeing that just in cooking, the higher the temperature, the quicker it cooks. And remembering that cooking is a reaction. So what's actually happening as we increase the rate of the temperature? Okay, so as we increase the temperature, think about our particle model. As we give those particles, or we transfer more energy to those particles, they move more. So how does that relate to our collision theory? They move more, there's more chance of them colliding. So by increasing the temperature, we increase the kinetic energy in those molecules. This means that the molecules move faster and collide more often. There are now more collisions occurring in the same amount of time because they have more energy, and therefore the greater number of collisions, the greater the proportion of successful collisions and the faster the reaction. So the effect of temperature. Chemical reactions slow down when they're cooled or speed up. All my animations are wrong, it looks like. Or speed up when they're heated. Okay, so we've got our particles here, and we've got one beaker at 2 degrees, so lower energy, lower kinetic energy in there, lower temperature, lower kinetic energy, so fewer collisions will be successful. If we increase the temperature, those particles start moving around more and quicker. So higher temperatures, more kinetic energy, more collisions, okay, and we've got more activation energy there to start those reactions. Alrighty, so we've looked at temperature, number 1. Number 2, we are looking at the concentration of reactants. Now, imagine we are at an airport, okay, and we're walking through the terminal. There's only 5 other people there, okay. Though 1 or 2 of them may find a way to get in your way, you're probably not going to collide. Now, on the other hand, imagine you're trying to walk through an airport terminal during school holiday times. It's peak time during the day. It's full of people. Okay, this is pre-COVID times. As a result, you're always nearly bumping into people, and it's causing you to have to react and move more and more. Well, it's the same with our particles. If you've got more particles that increase the concentration, you've got more chance for reaction. So what is concentration? Chemists use the term concentration to refer to the amount of reactants that are present in a given volume during the reaction. So if we have a look here, and we've got the particle models, we've got our 2 conical flasks. On the left hand side, we've got a higher concentration, so a concentrated solution, and you'll see there's more particles in that given area, that square. Then on the right hand side, where we've got a dilute solution, you'll see there's less particles. So the more reactants dissolved, the higher the concentration. The fewer reactants dissolved, the more dilute the concentration, or lesser concentration. Alright, so more reactants means there's more chance, so more particles of the reactants means there's more chance of collisions, okay, and there's less space between our particles. So again, we're seeing our concentrated solution and our dilute solution now. So what are the effects of concentration? So on the left hand side, we have few molecules, few collisions, the rate of reaction is low, and on the right we have many molecules, more collisions, the rate of reaction is greater. When you increase the concentration of reactants in a chemical reaction, there are more reactant molecules present, so they are more likely to bump into each other, resulting in our chemical reaction. Okay, so now thinking about our third point. So we've done temperature, we have done concentration, we're now looking at agitation, so stirring. We all know that stirring will make something dissolve faster. Think about stirring your Milo into your milk or sugar into the tea. If you stir it, then it dissolves faster. Yep. Whereas if you don't stir it, it doesn't dissolve as quick or stays at the bottom. The same happens if you're causing a reaction to occur. So the same happens for a rate of reaction. Without stirring the reactants, they'll become separated, they don't mix well together. This then reduces the number of collisions, so the rate of reaction will decrease. The products can also build up around the reactants as they form. This will mean there is less collisions between the reactant and particles as well. So quite often you'll see that if you have a metal reacting with a liquid, that the outside of the metal gets the product on it and then the reaction actually slows. When we stir the reaction mixture, it keeps everything moving around and therefore more chance of the reactants colliding. More collisions will mean greater chance of fruitful collisions, and therefore our rate of reaction increases. Okay, we have done temperature, we have done concentration, we have done agitation or stirring. We now move on to surface area of reactants. Ignore the bottom right hand corner, my graphics are wrong again. An object reacts more quickly if it's broken into smaller pieces. Okay, so we've got this diagram now, and the text would now make sense. We've got a large cube and we've got 4 smaller cubes, and as you can see we've got more surface area on the 4 smaller cubes because we've got all that inside area that we didn't have on the large one. So if we break our reactant into smaller pieces, we get more opportunity for reaction occur. Okay, and that's because small objects have a larger surface area for chemical reactions to occur. Imagine you put an Alka-Seltzer into water. Okay, if you just put the whole tablet in, it takes a while to dissolve. You crush it up and put it in, it will dissolve very quickly. Okay, so that's dissolving, but when we're looking at reactants, it's exactly the same. Reactions will occur faster if the solid reactions are ground up rather than one solid block. This is because the liquid reactant can react with more solid material as the surface area is increased. The liquid reactant being able to access more of the solid material, meaning there's more collisions occurring, so our reactions occur more quickly. So you can see there, you've got that one large solid on the left-hand side, or you've got broken up on the right-hand side with much more surface area. All right, we've done temperature, we've done concentration, we've done agitation, and we've done surface area. Our 5th factor that can increase or decrease the rate of reaction is using catalysts. What is a catalyst? A catalyst is a material that increases the rate of chemical reactions without being affected itself. So it's not used, it's not changed, so we say it's not consumed. Common examples of catalysts are platinum, which is used in automobile catalytic converters to convert carbon monoxide and nitrogen oxides to carbon dioxide and nitrogen. And also the enzymes in your body that cause biochemical reactions to proceed more quickly. So catalysts can be added to a reaction to make it proceed faster. They don't actually take part in the reaction. They're not used in the reaction. So at the end of it, there'll be the same mass of catalyst as there was at the start and after the reaction. Therefore, they're not actually included in the reactants, but they make the reaction go faster. They work by creating new pathways with lower activation energy for forming products. They're actually quite fascinating. It's kind of a bit like taking a shortcut. The reactants and products are the same, but the catalyst helps the reaction in such a way that more collisions between the reactants will be successful. So they kind of bring the reactants together to cause the reaction using less energy. So the activation energy, the amount of energy needed for the reaction to occur, remember, is lowered with a catalyst. And if you have a look in the graph, the blue is without a catalyst, the red is with a catalyst. So we're showing that, remembering those graphs are called those energy profile diagrams. So enzymes are biological catalysts, okay? Now, if you have a look at this, this is just an infographic, okay? We're not saying that it's actual frogs, but it just helps you get your mind around. Now, On the left-hand side, we've got the activation energy barrier, which is that high pile of rocks. It's really hard for our froggies to have enough energy to jump over there. Now, enzymes lower the barrier as such, and then it's much easier for our froggies to jump. It's just an infographic to get your mind round how these catalysts, which enzymes are one of, work. Okay, so thinking about enzymes, we've got lots and lots of reactions occurring in our body, which we call metabolic reactions, and they need to occur very quickly. So there's special proteins in our body that are called enzymes, and they act as catalysts, okay? Now, enzymes are critical in living organisms, okay? As with all other catalysts, they aren't used up in the reaction, so they can be used over and over again. There are enzymes in your saliva, so amylase in your mouth, that break down starch. And then there's all different enzymes all through your body. There's some in your stomach that break down proteins, and then there's lots in your intestines that are breaking down, digesting your food. And as you can see in the diagram, it's meaning that activation energy is much less, which is really important in living organisms because it's actually what maintains a set body temperature. Okay, so rates of reactions. The greater the number of successful collisions between particles, the faster the reaction will be. All factors that affect the rate of reaction do so by altering the number of collisions in a given period of time. Thank you for watching our third video on Chemistry 2, all about rates of reaction.